Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to Signals and Systems course. We're in chapter 1 and we're talking about module number 1, signals. This is the last section on this module, which is talking about signals, energy, and power. When we talk about energy and power, we have to differentiate between the total energy, which goes for the signal from minus infinity all the way to infinity, and between the average power, which does not consider the entire axis rather than an average over a unit of time. So let's say it is 1 second. So if I want to consider the energy of the signal over all the spectrum from minus infinity all the way to infinity, we call it total energy. And if we're considering it as an average over a unit of time, so the energy stored in this part over a unit of time, it's called average power. Starting with the energy, the total energy of continuous signal is given by this equation, where we have to consider from minus infinity all the way to infinity the square of absolute value of x. And if it was real, it will be simply x squared. And if it is not real, it is complex, then it will be x times x conjugate. And considering the integration, and for this example, we have to square this part. X clearly shown here, x of t is equal to 0 at this part. And similar, x of t will be equal to 0 at this part. So this integration will reduce from minus 1 to 1, and we have to take the square of this value. So this will be reduced to be as follows. So the e of this example is equal to integration from minus 1 to 1, and this is the square will be 0.25 dt. And as you know, the integration is nothing but the area under the curve, considering this is squared. So we will consider the height will be equal 0.25, and the width will be from minus 1 to 1, which is equal 2 times 0.25, and this will be equal to 0.5. Considering the discrete time signal, the integration will be changed or replaced by the summation from minus infinity to infinity, and x of t will be replaced by x of n. In fact, if the energy of the signal was finite, then we call it this signal, or we classify the signal as an energy signal. So this is meaning that it is finite energy. Just to take an example for discrete signals, we can say that x of n is defined by the following sequence. So let's say it is 3, minus 2, 0, and 1. And the 0 is located somewhere here. So we have just to simply square these values. So 3 will be 9, 2 will come to 4, and 0 will become 0, 1 will become 1, and then we just simply sum up these values, and this turns to be equal to 14. So in both cases, in continuous time, it is finite number, it is not reaching infinity, and it is not absolute 0. And in discrete time also it is 14, which is not 0 and not infinity. In both cases, both examples are energy signal. What happens if we're talking about periodic signals? As you know that the periodic signals repeat itself on each period. So if we find that this period has a certain energy E, and it is repeating itself as per this equation, so this means it is repeating itself. So in this case, uh, this has a finite value of x of t. Let's consider that we have calculate the energy under this area. So as you go on from minus infinity to plus infinity, the total energy stored in this will approach with this summation to infinity. So E of t will be going all the way to be at E of t prime approaching infinity. So this brings us out of that previous classification where E has to be finite. Now E is reaching to infinity. That's why we have to define the power or the average power of the signal. So for periodic signals, the average power is just simply similar expression for the energy here as t goes to infinity. And then for this side, we are considering that we are averaging over this t. So how we calculate this expressions, we just get the period and do the integration for one full period and then divide it by that period for continuous time, and similarly for discrete time, replacing the integration by summation. So for aperiodic signals, sometimes we can calculate the average power because the energy reaches infinity. So we can use a similar approach for continuous time, but just letting t approach infinity. And similarly, we can do it for the discrete time signals and approaching. Let's make n approaches infinity. So to conclude, we can call a signal a power signal if the average power is finite. So P is finite number. It is not zero and it is not infinity. So it is a finite number. Then we call this signal a power signal. To summarize what we have discussed today, we have three important classes of signals. The first one is the energy signal, in which the energy is finite, so E is finite number. And the second category, where it is called power signals, where power is finite. And the third category, neither energy nor power is finite. And one clear example is x of t is equal to t. Both P approaches infinity and E also approaches infinity. I will leave for you these few examples here to practice at your own time. This is the first example where it is exponential times unit step function. And this is just simply a step function. And this is a periodic signals. I just left it for you to practice at your own time. By this, we are concluding this module, and we have went through the different sections of this signals, and the subjects covered in it was going from basic signals to the classification and properties of these signals, and then moving to the signals transformations and operation, and finally the power and energy signal subject. Thank you for your attention, and see you in the next time. Assalamu alaikum wa rahmatullahi wa barakatuh.